This is Dr. Cynthia Furse at the University of Utah, and today we're going to go over the node voltage method. The node voltage method is going to be an addition to our circuit analysis toolbox, and in fact, it's going to use two of the methods that we have previously developed in order to create the node voltage method. Let's first consider the difference between node voltage and voltage difference. Let's suppose we wanted to take a little hike up to the top of Mount Olympus. We would start in Salt Lake City, and we would hike to our first vantage point, and then we would come down to our second vantage point, up to our third, down to our fourth, and so on until we completed our hike back to ground in Salt Lake City. The voltage differences are the red lines, and they show the track that we actually take going up and down the mountain. Node voltage shows where we end up at any given point, the vantage points, the black V1, V2, V3, and so on. We actually have equations for these. We can say that V1 minus V0 is our first voltage difference, V2 minus V1 is our second voltage difference, and so on, and we can combine them to tell us that V2 minus V0, so the difference between here and here, for example, would be our first trip up and our second trip down. If these were electric circuits, we would know that each of those voltage differences are equal to IR. That's basically from Ohm's law. There are two different types of node voltage equations that we would do in this case. One is a simple case where we would say VA minus VB is equal to IR, but if we want to calculate the current, we can just bring the R over to the other side. If we had two resistors in series in this branch, we could simply add them up on the bottom in order to calculate the current through that branch. The other method that we use is Kirchhoff's current law, which says that all of the incoming currents are equal to the outgoing currents. We've seen that in other cases, and certainly we see this in the Provo River up by Heber as well, that at each of the nodes, the currents that come in equal the currents that go out, and there are several nodes in this circuit. Now let's do a simple node voltage example. In the case of node voltage, the first thing that we do is define a ground or a reference point. This is VG equals 0. That's our ground point. And then we define at each of our nodes all of the currents going out. Define the outward going currents. And then we'll write an equation for each of those outward going currents, adding them up to 0. That's what this first equation is going to be. All right, this first current right here is going to be VB minus VA divided by R1. That's right here. The second current is going to be VB minus VG divided by R4, right here. The third is VB minus VC divided by the sum of these two resistors, and that part's right here. That's our first equation. That's at our first node. Then we need another equation which says that VG is equal to 0. That's by definition. We defined that to be 0. And then we need to write equations for the two nodes that have the sources attached. We can write it this way as VA minus VG is equal to the voltage source, and VC minus VG is equal to the voltage source, but most of the time we can just look at this and say VA is equal to VS1 and VC is equal to VS2. Now we'd be ready to put those into a matrix equation to solve for our unknowns. What are our unknowns in this case? It's not the current. You actually don't see current as listed as a variable in any of these equations. The unknowns are our node voltages VA, VB, and VC, except of course that VA and VB are known because of these two equations. There are basically three types of branches, and in fact I'm also going to show you a fourth method. So the first one is a simple case that just has a single resistor. That's right here. The second is another simple case that has a series of resistors. The third is a simple voltage source, and the fourth is a simple current source. There is one other one, and that's going to show up in our next problem, so I'm just going to draw it here. That's when we have a source attached to a resistor. In this case, one of the things that you can do is move the resistor around, because it doesn't matter what order the voltage source and the resistor are, and then you can put a node in between them as needed. Okay, here are the steps to performing node voltage analysis. First, identify all the extraordinary nodes or the critical nodes. The critical node, for example, would be in between this voltage source and this resistor, we need to put a node right there. The extraordinary nodes, of course, are any place that you have three or more things coming together. Then we select one of these nodes as a ground or reference node. VG is equal to 0. Assign variable names to all of the other nodes and write the node equations for each node. Then we solve the system of equations for the node voltage. So basically, this method is going to give us the node voltages. We called those VA and VB when we were talking about our circuit analysis toolbox before. These are node voltages. And what we know here has to be, we have to know one node. So we need to know our ground node, and then we also need to know all of our resistors, and we can use the node voltage method to give us the node voltage equation, to give us the nodal voltages. Let's do this example. Okay, I'm going to change to red. So we've defined our ground right here. That's the ground of our circuit, and we've identified our extraordinary nodes, that's VA and VB, but we have this one more node here. I'm going to switch the resistance R3 and put it up here, making this now a short circuit, so that I can put another node right there, VC. That's going to make this problem easier. Now let's do the currents at each of the nodes that we've defined. Remember, we always define them as going out. Here are the outward going currents. So our first equation is going to come here. IS is coming in, and so we make it minus IS going out. Then we'll have plus VA minus VG divided by R1. That's this current right here. This current is going to be plus VA minus VB divided by R4, and that's equal to 0. Now let's do our second node. Our second node, we're also going to define all the currents going out. You might say, wait a minute, what about these two right here? Notice that in one case I define it as going from left to right, and the other case from right to left. This is okay because we are not actually defining any of these currents as variables. We're using the relative voltages instead. So let's go back to this one. So we're going to say, what would that current be? It would be VB minus VA divided by R4, plus what's going down there is VB minus VG divided by R2, and then what's going across this way, plus VB minus VC divided by R3, and that is going to be equal to 0. Now, does it always end up being 0? Yes, it does. It always ends up being 0 because we are adding all of the outward going currents. Good. Now, what other equations do we need? We know that VG is equal to 0, and then we also need to take care of this voltage source. So we can see that VS and VC are the same, or we could have written VC minus VG is equal to VS, but basically VC is equal to VS. Now let's put these into a matrix. What are my unknowns in this case? I need to find VA and VB. Let's leave VC as unknown, and I'll show you how it would work out. So VA, VB, and VC are going to be my unknowns, and I will have a 3 by 3 matrix where the columns will be related to VA, VB, and VC, and then over here I'll have a vector of constants. So let's take my first equation. I'm going to move my IS over here, and then I need to know what is multiplied by VA. It is 1 divided by R1. My VG is 0, so I can just set that equal to 0. And then, what do I have here? I have another part of my VA, 1 divided by R4. What's multiplied by VB? Minus 1 over R4. And what's multiplied, make that kind of a little clearer there for you, what's multiplied by VC? 0. And then over here I have minus IS has turned into plus IS because I put it on the other side of the equation. Okay, now let's do this one. What's multiplied by VA is 1 over R4 negative. What do I have for VB? The R2 and R4, so it's 1 over R4 plus 1 over R2 is multiplied by VB, and then, I also have plus 1 over R3, and then what's multiplied by VC? Minus 1 over R3. Do I have any constants? No. Then over on this side, what can I say about VC? I can say that 1 times VC is equal to Vs. Now I could put this into my calculator or MATLAB and be able to solve for it. Let's do another equation. Let's do another example. I'm going to just switch to another video to do that example.